The universe is a story told not just in the brilliant ink of stars, but in the profound, unsettling blankness between the words. We spend our lives bathed in light, in sound, in substance. We are creatures of presence, defining ourselves by what we can see, what we can touch, what we can measure. But the cosmos, in its infinite and often terrifying wisdom, is built upon a very different architecture. Its grandest statements are frequently made not with a shout, but with a silence so complete it borders on the absolute. It is a silence that stretches across distances. Your mind cannot truly hold a quietude that predates the very first atoms. What happens when you stare into that silence? What does true cosmic absence really signify? We think we know emptiness. You may have felt a shadow of it standing on a desolate shore at midnight with the ocean stretching out into an endless black mirror. Perhaps you've sensed it flying high above the clouds, looking down upon a world that seems distant and abstract. But these are illusions of emptiness, fleeting moments of isolation. Even in the deepest vacuum we can create on Earth, stray atoms stubbornly refuse to leave. In the deepest reaches of interplanetary space, the sun's breath, the solar wind still whispers past. Even between the stars of our own galaxy, gossamer clouds of hydrogen, and the faint ghostly light of 100 billion distant suns fill the void. There is always something, a background hum of existence, the echo of creation itself. The cosmic microwave background radiation bathes everything, a perpetual faint glow left over from the Big Bang. It is the universe's oldest light, a testament that even the dark is not truly dark. To find a genuine void, you must leave all of this behind. You must travel beyond the familiar spiral arms of the Milky Way, past the ghostly halos of our neighbouring galaxies, the Andromeda and Triangulum. You must push out further and further until our own local group of galaxies is nothing but a forgotten speck of light in your rearview mirror. Out here, hundreds of millions of light years from home, the universe finally reveals its true large-scale structure. And it is nothing like the uniform starfield we imagine. It is a magnificent, impossible tapestry, a cosmic web. Imagine flying through it. You would see that galaxies are not scattered randomly like dust motes. Instead, they are drawn together by the relentless invisible hand of gravity into colossal shimmering structures. Luminous filaments of galaxies billions of light years long stretch across the darkness like threads spun from captured light. These threads twist and braid together, forming vast flattened walls, celestial supercontinents of matter. Where these filaments and walls intersect, the universe becomes a frenzy of creation. Here you find the great clusters and superclusters, the bustling gravitational downtowns of the cosmos. These are the cosmic metropolises, home to thousands of galaxies, all caught in a swirling, intricate dance. They are ablaze with the light of trillions of stars, roaring with the radiation of supermassive black holes, and saturated with the mysterious unseen presence of dark matter. This is where the universe is most alive. This is where the story of cosmic evolution is written in fire. But this structure, this brilliant web, is only half the picture. For in between these filaments of light, in the vast spaces they enclose, lie the voids. These are regions of profound underdensity, cosmic deserts sparsely populated and hauntingly quiet. The average void is 100 million light-years across a space so immense that if our Milky Way were situated in its centre, we would see almost nothing in our night sky. The familiar constellations would be gone. The sky would be a near-perfect black, punctuated only by the pinpricks of a few lonely isolated galaxies, cosmic hermits living out their lives in the quietest neighbourhoods of the universe. For decades, astronomers have mapped these voids. They are a natural and expected consequence of gravity. As gravity pulls matter together to form the filaments and clusters, it inevitably leaves other regions depleted. The voids are the spaces from which the building materials of the universe have been scavenged. They are the quiet countrysides to the great galactic cities, and for a long time we believed we understood them. They were big, they were empty, but they fit our models. They were a predictable part of the grand cosmic architecture. The universe, for all its majesty, seemed to adhere to its own rules, until we looked toward the Swan. Come back home for a moment to a warm summer night on Earth. Look up and you can trace its shape among the stars, Cygnus the Swan flying south along the river of the Milky Way. Its brightest star, Deneb, forms one corner of the famous summer triangle, a celestial landmark for stargazers for millennia. The constellation is an ancient friend, a familiar pattern woven into our myths and our memories. To the naked eye, it appears as a place of incredible richness. The dense star fields of our galaxy's spiral arm run directly through it, creating a lane of faint shimmering light. Telescopes reveal it to be a treasure trove of celestial wonders, glowing nebulae where new stars are being born, the turbulent remnants of exploded suns, and the first black hole ever confirmed, Cygnus X1. It is a place of life, of violence, of cosmic abundance. It felt like a region we knew a well-trodden path in the sky. It was precisely this richness, this density of nearby stars that made it the perfect place for a new kind of search. Not a search for what was far away, but for what was close. The Kepler Space Telescope was launched with a single revolutionary purpose: to find planets orbiting other stars. To do this, it would not scan the whole sky, but would instead stare unblinking at one tiny patch of it. A patch located right between the swan's outstretched wings. For 4 years, Kepler's sensitive eye remained fixed on this single field of view, an area of the sky no bigger than your outstretched hand. It watched 150,000 stars for the telltale dimming that would betray the presence of a transiting planet. It was a mission focused on the immediate neighbourhood on the foreground of the cosmic masterpiece. But science often finds what it is not looking for. While Kepler was busy discovering thousands of new worlds, other astronomers began to use its vast dataset for a different purpose. They weren't interested in the bright nearby stars Kepler was monitoring. They wanted to see what lay behind them. They were looking for the faint ghostly smudges of distant galaxies billions of light years away that happened to reside in the same line of sight. By counting these background galaxies, they could build a 3-dimensional map of the deep universe in that direction, a core sample drilled directly through the cosmos. The process was painstaking. They had to carefully filter out the light from all the foreground stars, like trying to hear a whisper in a hurricane. But as the data slowly accumulated, a strange and unsettling picture began to emerge. The counts were wrong, dramatically wrong. In other deep field surveys of the universe, when we point our telescopes at a random patch of sky, we expect to see a certain density of distant galaxies. The cosmic web on its larger scales should be roughly the same everywhere. There should be filaments walls and the normal well-behaved voids in between. But here in the direction of Cygnus, something was different. As the astronomers peered deeper and deeper into the data beyond the familiar stars of our own galaxy, they found nothing. A profound, gaping, inexplicable nothing. The faint smudges of background galaxies that should have been there, the distant filaments of the cosmic web, were simply gone. It was as if someone had taken a giant celestial eraser and wiped the universe clean. At first they suspected an error. Perhaps vast clouds of interstellar dust within our own Milky Way were blocking the view, drawing a dark curtain over the distant cosmos. But observation after observation in different wavelengths of light showed this wasn't the case. The view was crystal clear. There was no curtain. There was just absence. This was not one of the ordinary voids that pepper the cosmos. This was a monster. A region of space so vast and so empty it defies our understanding. Stretching for nearly 2 billion light years, it is a chasm of such epic proportions that light itself, the fastest thing in creation, would need 2 billion years to cross from one side to the other. You could fit 20,000 Milky Way galaxies end to end across its breadth, and still have room to spare. Inside this colossal volume, the cosmic web has not just thinned out, it has failed. It is a zone of staggering cosmic poverty, possessing only a tiny fraction of the matter we would expect to find there. It is a gravitational ghost town on an unimaginable scale. We call it the Kepler Void, named for the telescope whose gaze inadvertently uncovered it. But a name does little to tame the sheer vertigo of its existence. It is a hole in the fabric of the universe, a wound in the tapestry of creation, and it presents us with a terrifying, exhilarating problem. It shouldn't be there. According to our best models of cosmology, the laws of physics as we understand them simply do not allow for the formation of a void this large and this empty. Gravity acting over the 13.8 billion years since the Big Bang has had enough time to build the great superclusters and filaments we see, and to sweep out the normal smaller voids. But it has not had nearly enough time to excavate a cavity of this magnitude, To create the Kepler Void would require a force, a process, or a history that is not in our textbooks. It is a piece of the puzzle that doesn't just fit awkwardly, it seems to come from an entirely different puzzle box. It stares back at us from the heart of the Swan, a silent refutation of our most cherished theories about how the universe works. How does such an anomaly form? Is it a bizarre primordial relic, a cold spot from the universe's infancy that somehow survived to the present day? Is it evidence of some new exotic physics like the influence of a neighbouring universe pushing against our own? Or is it a scar left behind by a cataclysmic event on a scale we have never dared to imagine? The Kepler Void is more than just an empty space. It is a question mark written in the language of absence demanding an answer. To find it, we must leave the safety of the known and venture forth not into the light, but into the deepest darkness our telescopes have ever found. We must journey into its silent, starless heart. The familiar tapestry of the night sky is a beautiful lie. Not a malicious one, but a deception of perspective, a grand illusion painted on the dome of our perception. From our small terrestrial vantage point, the stars seem scattered with a poet's carelessness, a handful of celestial diamonds thrown across black velvet. We connect them into patterns, into heroes and mythical beasts, imposing a familiar order on what appears to be a random two-dimensional display. For millennia, this was our universe, a flat map of brilliant points. But this map, we now know, conceals a staggering, almost unimaginable depth. It hides a structure so vast, so intricate, that the mind struggles to contain it. If we could pull back, moving faster than light itself, leaving our galaxy and then our local group of galaxies behind, we would witness the flat star field resolve into something else entirely. We would see the true architecture of the cosmos unfurl. Gone would be the simple notion of galaxies sprinkled evenly through space. In its place, a colossal, luminous structure would materialize a web of impossible scale that permeates everything. This is the cosmic web, the universe's hidden skeleton. It is the grandest prediction of our standard model of cosmology, the theory we call lambda CDM. This model is more than a set of equations. It is our cosmic origin story, painstakingly written in the language of physics and confirmed by decades of observation. It tells us that in the moments after the Big Bang, the universe was an almost perfectly smooth, hot, dense soup of matter and energy. But not perfectly smooth. There were quantum fluctuations, tiny, almost infinitesimal variations in density. And over 13.8 billion years, gravity, the universe's master sculptor, went to work on those imperfections. Imagine gravity as a tireless patient artist working on a cosmic scale. Its influence is relentless. Where there was slightly more matter, gravity pulled in, more amplifying those initial tiny seeds of structure. Dark matter, that mysterious invisible substance that outweighs all the normal matter we can see, formed the primary scaffolding. It collapsed into immense invisible halos, creating gravitational wells that ordinary matter, the stuff of stars, planets and ourselves, could then fall into. Over eons, this process wasn't random. It was organised. The matter didn't just clump. It was pulled and stretched into immense interconnected strands, forming the breathtaking structure we now call the cosmic web. These are not threads of silk, but rivers of galaxies flowing through the dark. We call them filaments. Stretching for hundreds of millions of light years, these are the glowing arteries of the universe, incandescent with the light of trillions upon trillions of stars, all bound together by the invisible grip of dark matter. They are the great highways of the cosmos, channeling material and fueling the growth of galaxies along their lengths. Follow one of these filaments and you travel through a realm of breathtaking density and activity. And where these filaments intersect, where the cosmic rivers converge, you find something even more spectacular: the great galaxy clusters. These are the metropolises of the universe. Bustling, chaotic and violent, a cluster can contain thousands of galaxies, all whirling around a common centre of gravity at incredible speeds. They are cosmic cities bathed in the glow of X-rays from superheated gas, where galaxies collide and merge in gravitational ballets of creation and destruction. Here, in these dazzling nodes of the cosmic web, the universe is at its most brilliant, its most concentrated, its most alive. For a long time, our telescopes, naturally drawn to the light, focused on these filaments and clusters. They were the obvious shining components of the grand design. But the story told by the Lambda CDM model, our great cosmic narrative, insisted that the filaments and clusters were only half of the picture. The most profound part of the structure wasn't what was there, but what wasn't. Between the luminous filaments in the vast expanses separating the great clusters lie the cosmic voids. If the clusters are the universe's roaring cities, the voids are its silent, forgotten countryside. These are regions of profound underdensity, the largest and most mysterious structures in the cosmos. They are not, as their name might suggest, perfect vacuums of absolute nothingness. That kind of purity doesn't exist in our universe. Rather, they are places where the process of structure formation has run in reverse. While gravity was pulling matter together to build the filaments, it was simultaneously emptying out these other regions. The voids are the cosmic leftovers, the material that escaped the great gravitational roundup. They are the quiet, dark spaces from which matter has been evacuated over billions of years, leaving behind a state of near-perfect solitude. Our models give us a very clear picture of what a typical void should be like. They should be enormous, spanning anywhere from 30 million to over 300 million light-years in diameter, dwarfing even the largest superclusters. Within their immense volumes, we expect to find very little. Perhaps a few small, lonely and underdeveloped galaxies known as void galaxies drifting like ghost ships in a dark ocean. These galaxies are fascinating in their own right, pristine examples of what galactic evolution looks like without the constant gravitational harassment and mergers found in denser environments. Looking through a void should also have a measurable effect on the oldest light in the universe, the cosmic microwave background radiation. The expansion of space within these underdense regions should leave a faint cold imprint on that ancient light, a subtle signature of the emptiness it has traversed. Voids, therefore, are not just empty space, they are active components of the cosmic structure. They are the dark counterpoint to the bright web, the yin to its yang. Their sheer volume is staggering. They make up the vast majority of the universe's real estate. We live on a planet orbiting a star in a galaxy, which is itself part of a filament. Our entire existence is nestled within the bright, busy parts of the web. But the true dominant geography of the cosmos is this profound emptiness. Understanding the voids, their size, their shape, their degree of emptiness is as crucial to testing our cosmological models as understanding the clusters. They are the ultimate test of our theories about gravity, dark matter, and the dark energy that is accelerating the expansion of the universe itself. They are the quiet arbiters of our cosmic story, and so we map them. With painstaking surveys, we plot the positions of millions of galaxies in 3 dimensions, slowly piece by piece, revealing the filaments and clusters, and by extension outlining the shapes of the great voids that they surround. We were building a confident picture, a grand atlas of our local universe. The voids we found were vast and empty, just as predicted. They were lonely, just as predicted. They were cold, just as predicted. Our story of the cosmos, the Lambda CDM model, seemed to hold up beautifully. It appeared we had a firm grasp on the rules that governed the universe's grand architecture. There was no reason to suspect that any particular patch of sky, any direction we chose to look, would hide an anomaly so profound it would challenge the comfortable narrative we had built. And then our attention was drawn to a familiar friend in the summer sky of the northern hemisphere. The constellation Cygnus the Swan. For centuries, Cygnus has been a celestial landmark, its brightest star Deneb, forming one corner of the famous summer triangle. It's an area rich with nebulae and star-forming regions, a beautiful and seemingly well-understood piece of our own Milky Way galaxy. It was here in this specific direction that humanity decided to conduct one of the most ambitious and focused searches in the history of astronomy. This wasn't a grand survey to map the universe, but a mission with a much more intimate and perhaps more profound goal to find other worlds. In 2009, NASA launched the Kepler Space Telescope, an observatory with a singular, unblinking purpose. Its mission was to stare relentlessly and without interruption at a single patch of sky within the constellation Cygnus. Kepler was not designed to see the grand cosmic web. Its gaze was fixed on a field of about 150,000 nearby stars, all within our own galactic backyard. It was a cosmic census taker, not a cosmic cartographer. Its method was one of sublime patience. For 4 years, its sensitive photometer monitored the light from these stars with unprecedented precision, looking for the tiniest, most subtle dips in their brightness. It was searching for transits the minuscule shadow cast when a planet from our perspective passes in front of its parent star. This was a hunt for needles in a cosmic haystack requiring a stability and focus never before achieved. Kepler's unblinking eye had to be sensitive enough to detect a change in brightness, equivalent to a gnat flying in front of a distant searchlight. The mission was a staggering success. It revolutionized our understanding of planets beyond our solar system. Kepler found thousands of candidate worlds revealing that planets are not the exception but the rule. It showed us that small rocky worlds like our own are common throughout the galaxy. It transformed exoplanets from a fringe topic of science fiction into a mainstream data-rich field of astronomy. The Kepler field, that small rectangle of sky between the stars Deneb and Vega, became the most intensely studied patch of stellar real estate in human history. We knew its stars, their properties, their ages, and thanks to Kepler, we knew about the thousands of worlds orbiting them. We had a hyper-detailed map of the local neighbourhood in that direction, a perfect family portrait of one corner of our galaxy. But the universe, of course, does not stop at the edge of the Kepler field. Beyond those 150,000 stars beyond the edge of our own Milky Way lies the vast expanse of intergalactic space, filled with other galaxies and the great dark voids between them. Kepler itself could not see this. Its mission was focused on the foreground. It was blind to the grand structures lying in the deep background. While Kepler was patiently hunting for planets, other astronomical projects were engaged in the more traditional work of mapping the universe's large-scale structure. Surveys like the Sloan Digital Sky Survey were systematically charting the positions of millions of galaxies across the entire sky, building up the three-dimensional map that revealed the cosmic web. And this is where the story takes its unexpected turn. This is where two very different kinds of exploration, one looking deep into our galaxy, the other looking far beyond it, would eventually intersect to reveal something deeply unsettling. As astronomers used these large-scale surveys to map the universe in the same direction that Kepler had been staring, they began to notice something was wrong. They were charting the filaments and clusters connecting the dots of the cosmic web. But in that specific direction, behind the familiar stars of Cygnus, behind the thousands of new worlds Kepler had gifted us, the galaxies simply stopped. It wasn't a gradual thinning out. It was a stark, unnerving deficit. Where the models predicted highways of galaxies, there was only a scattering of lonely travellers. Where the great cosmic atlas should have shown a landscape rich with structure, the map had a gaping, inexplicable hole. The data from these other surveys, which measured the distances to faraway galaxies, provided the crucial third dimension that Kepler's flat, two-dimensional field of view lacked. It was like having a perfect high-resolution photograph of the trees at the edge of a forest, only to discover from a different vantage point that the entire mountain range that was supposed to be behind them had vanished. The detailed knowledge of the foreground provided by Kepler only made the emptiness of the background more jarring and more profound. The sheer coincidence was staggering. Of all the patches of sky Kepler could have stared at, it happened to be pointed directly towards a region of space that defied our expectations in the most fundamental way. The telescope's primary mission had nothing to do with cosmology or the large-scale structure of the universe, and yet its legacy would become inextricably linked to this burgeoning mystery. The intense scrutiny of the Kepler field gave this particular direction in space a name and identity. The anomaly, this colossal region of unexpected emptiness lurking behind the swan, was christened the Kepler Void. But this was no ordinary void. The voids predicted by our models are underdense, not completely empty. They are vast, but they obey certain rules of scale and population. The initial data hinted that the darkness in the heart of Cygnus was different. It seemed larger, deeper, and more profoundly desolate than it had any right to be. It was a pocket of the universe that seemed to have been carved out with a precision that our theories could not easily explain. Was it a statistical fluke, a trick of the data from the early surveys, or was it a genuine feature of the cosmos, a structure that hinted at a flaw in our grand story of the universe? A new chapter of cosmic exploration was beginning, one that would force us to peer into this unexpected darkness and question the very foundations of what we thought we knew. The swan, it turned out, was hiding a secret, a profound and silent abyss, and we had only just begun to comprehend its chilling scale. The initial data felt like a betrayal of physics itself. A digital ghost haunting the Kepler mission's archives, a stain of nothingness spread across a field of view that was meant to be teeming with the promise of worlds. For the handful of astronomers who first stumbled upon it, the immediate instinctual reaction was not excitement, but a cold professional dread. Something had to be wrong. The universe as we understood it simply did not permit such a colossal pocket of emptiness to exist. Science, after all, is built upon a foundation of skepticism. Extraordinary claims demand truly extraordinary evidence, and the claim of a 2 billion light-year hole in the cosmos was perhaps the most extraordinary of them all. The first wave of suspicion fell naturally on the instrument. Was one of Kepler's photometers malfunctioning? Could a subtle, uncorrected distortion in its optics be creating a phantom void where none actually was? The engineering teams were summoned, diagnostics were run, and the telescope's health was triple-checked. The verdict came back clear and unsettling. Kepler was fine. It was reporting exactly what it was seeing. The blame then shifted to our own galactic neighbourhood. Perhaps we weren't looking through a window into deep space, but staring at a wall much closer to home. A vast, uncatalogued cloud of interstellar dust, a thick, clumpy fog of gas and microscopic grains could be obscuring the light from galaxies far beyond. This was a plausible, almost comforting explanation. It would make the Kepler Void a local phenomenon, an obstruction not a fundamental feature of the universe. To test this, astronomers turned to different wavelengths of light. Infrared telescopes capable of peering through cosmic dust, like a thermal camera cutting through smoke, were aimed at the heart of the Cygnus constellation. They scanned the darkness, searching for the faint warm glow that any foreground cloud of material would inevitably emit. They waited for the data to resolve into a familiar shape, a confirmation that would return the universe to its senses. But the infrared eyes of our most powerful observatories saw exactly what Kepler had seen. Nothing. No intervening nebula, no celestial smokescreen. The path was clear. The darkness was not a curtain drawn before the stage. It was the stage itself. With the simple explanations stripped away one by one, the scientific community was forced to confront the abyss. The initial whispers of a data glitch now had to become a formal, rigorous campaign of cosmic cartography. The time had come to measure the monster. The first line of defense against such an anomaly, the most basic tool in the cosmological arsenal, was a simple, brutal and painstaking head count. The Sloan Digital Sky Survey, a monumental effort to map a quarter of the entire sky, became the first arbiter. Its vast database, a celestial census of hundreds of millions of galaxies, was queried with a new and urgent purpose. Astronomers began the tedious work of drawing a boundary around the suspected void and simply counting the smudges of light, inside the circle versus outside. It was cosmic accounting on the grandest of scales. Imagine dedicating your life to finding things, to cataloguing the brilliant furniture of the universe, only to be tasked with meticulously proving a negative. Each galaxy plotted on the map's periphery only served to sharpen the edges of the emptiness within. The work was slow, a pointillist painting of absence. Days bled into weeks as supercomputers cross-referenced catalogues, eliminating foreground stars and distant ambiguous quasars. The emerging picture was starker than anyone had dared to imagine. Where the standard models of cosmic structure predicted thousands upon thousands of galaxies, should be the survey found only a few dozen lonely stragglers. The deficit was not a subtle statistical dip, it was a catastrophic near-total failure of galactic formation. This initial count confirmed the void's two-dimensional existence, its terrifying breadth on the canvas of the sky. But a photograph, no matter how barren, is profoundly deceptive. It flattens reality-collapsing depth into a single plane. Was this a true spherical chasm punched through the cosmos, or was it merely a long, thin and less remarkable tunnel, pointed directly at Earth by sheer cosmic coincidence? A bowling alley void would be a statistical curiosity, but a genuine sphere of nothingness, billions of light years across, would be a crisis. To know the difference, we had to add the third dimension. We had to measure its depth, and for that we needed to listen to the Song of Light itself. Every galaxy broadcasts its own story through its spectrum, and encoded within that light is a secret of its motion. As the universe expands, it stretches everything within it, including the very waves of light travelling through space. Light from a galaxy moving away from us is stretched, shifting its colour towards the red end of the spectrum. This is redshift, the universe's own speedometer and yardstick. The greater the redshift, the faster the galaxy is receding, and therefore the farther away it is in cosmic time and space. This technique would allow astronomers to build a 3D map to transform their flat image of absence into a true architecture. A new campaign began this time using the world's largest telescopes. Their giant mirrors aim like listening dishes at the few faint lonely galaxies that dotted the void's interior and its far distant boundary. The goal was to capture enough of their feeble light to surgically dissect it, with a spectrograph measuring the precise redshift for each one. Every single measurement was a monumental undertaking. Hours of precious telescope time would be spent staring at a single, barely there smudge, patiently gathering photons that had travelled for eons across the most desolate landscape in the known universe. It was like trying to hear a whisper from across an ocean. The first results trickled in, then poured. Each data point was a pin dropped onto a three-dimensional cosmic chart. The galaxies on the near side of the void showed a certain redshift, placing them at a distance of, say, 4 billion light-years. Then there was nothing, an immense gap in the data. No galaxies, no signals, no redshifts to measure. Just a silent, gaping hole in the cosmic distribution. Finally, on the far side of that immense silence, the telescopes began to pick up signals again. Faint ancient galaxies with vastly higher redshifts, placing them perhaps 6 or 7 billion light-years away. The bowling alley hypothesis was shattered. This was not a tunnel, it was a chasm. The data, when fully assembled, was breathtaking and terrifying. It gave the Kepler Void its true stomach-churning dimensions. A cavity in the cosmic web nearly 2 billion light-years deep, so vast that our own Milky Way galaxy, with its hundreds of billions of stars, would be like a single grain of sand lost inside an empty stadium. Light itself, the fastest thing in the universe, would require the entire lifespan of Earth's complex life just to make the journey from one side to the other. The sheer soul-crushing scale of it began to sink in. The scientific community, once so skeptical, was now in quiet awe. The evidence from galaxy counts and redshift surveys was overwhelming. The void was real, it was ancient, and it was bigger than our theories allowed. But there was one final spectacular test to be performed, a way to ask the universe itself if this wound had been there since the very beginning of time. To do this, scientists had to look past the galaxies, past everything, all the way back to the faint residual glow of the Big Bang itself. This is the cosmic microwave background, or CMB. The baby picture of the universe, an echo of creation imprinted on the sky when the cosmos was just 380,000 years old. This ancient light is astonishingly uniform, the same temperature in all directions to an incredible degree. But it isn't perfect. Tiny, minuscule fluctuations in its temperature, hot spots and cold spots, just a few millionths of a degree different, betray the seeds of all future structure. The hot spots are where matter was slightly denser, the kernels that would one day grow into the great superclusters of galaxies. The cold spots were slightly less dense, the cradles that would evolve into the cosmic voids. There is a subtle, almost magical way that a massive structure, or a massive lack of structure, can leave a fingerprint on this ancient light as it passes through. It's a phenomenon known as the integrated Sachs-Wolf effect. Imagine a single photon of CMB light a particle from the dawn of time on its 13 billion year journey towards Earth. As it falls into the gravitational well of a supercluster of galaxies, it gains a tiny bit of energy, becoming infinitesimally hotter or bluer. As it climbs back out of that same gravitational well, it loses that exact same amount of energy, becoming cooler or redder again. The net effect is zero. The photon emerges unchanged. But something very different happens when it crosses a colossal void. A supervoid, like the one discovered by Kepler, isn't just an absence of matter. It is a place where the expansion of the universe itself, driven by the mysterious force of dark energy, is more dominant. It is an expanding bubble within an expanding universe. So as our ancient photon enters the void, it falls down a very shallow gravitational slope and gains a little bit of energy, becoming slightly bluer. But while the photon is inside trekking for 1 billion years or more, the void itself expands and stretches out beneath it. The gravitational slope it has to climb to get out is now even shallower and flatter than the one it fell down. It loses less energy on the way out than it gained on the way in. The photon escapes with a net gain of coolness. It emerges ever so slightly redder and colder than it began. The prediction was clear, direct and falsifiable. If the Kepler Void was truly a gargantuan ancient structure, then it must be leaving a giant anomalous cold spot on the cosmic microwave background. A thermal bruise on the afterglow of creation itself. The teams turned to the data from our most sensitive CMB maps, from the Planck and WMAP space telescopes. They knew the precise coordinates of the Kepler Void. Now they had to check if that exact location on the sky corresponded to one of the coldest spots in the entire CMB map. It was the ultimate moment of truth, a confrontation between the universe we see today and the universe as it was in its infancy. The computer overlaid the map of the void traced by the galaxies onto the thermal map of the primeval universe, and there it was, a perfect chilling alignment. In the precise direction of the Kepler Void, the CMB was significantly colder than the average. It wasn't just any cold spot. It was one of the most prominent and statistically significant cold anomalies ever detected. The smoking gun. The final irrefutable piece of evidence. The void was not an illusion. It was not a data error. It was a real physical entity of unimaginable proportions, and it had been gravitationally altering the path of ancient light for billions upon billions of years. The debate was over. The skepticism, once a raging fire, had dwindled to the embers of stunned acceptance. The painstaking process of scientific validation was complete. But the end of one mystery was merely the beginning of a much larger one. Because in proving the void existed, astronomers had broken their own models, the standard model of cosmology. Our best and most complete description of the universe is built around a concept called the cosmological principle. The idea that on large enough scales the universe is homogeneous and isotropic, essentially that it looks roughly the same everywhere and in every direction. Pockets of structure are expected, of course. The cosmic web with its filaments of galaxies and its intervening voids is a natural consequence of gravity, acting on tiny quantum fluctuations over the course of 13.8 billion years. We can even simulate this process. On our most powerful supercomputers, we can create virtual universes inputting the known laws of physics, gravity, dark matter, dark energy, and letting them evolve from a smooth hot Big Bang into the lumpy structured cosmos we see today. These simulations are remarkably successful. They produce virtual cosmic webs that look astonishingly like the real one. They create filaments, clusters, and voids of all different shapes and sizes, but they almost never ever produce a Kepler void. Out of thousands of simulated universes, a void of this magnitude, this empty and this gargantuan, appears so rarely that its existence in our own reality becomes a statistical nightmare. It is a 1 in a billion anomaly. An outlier of such extreme proportions that it strains the very definition of a fluke. This is where the true terror of the discovery lies. The Kepler Void is not just a place, it is a paradox. It is a feature of our universe that our best theory of the universe says should not exist. It stands as a silent, colossal rebuke to our understanding. A question mark written in the language of nothingness, spanning 1/10 of the observable horizon. Does its existence mean our theory of gravity is incomplete? That on the larger scales it behaves in some strange repulsive way we cannot yet fathom? Could it be the signature of some exotic new physics, a remnant of a collision with another universe in the distant past? Or is there something fundamentally wrong with our assumptions about dark energy, the very force that is accelerating the cosmic expansion and carving out these empty spaces to begin with? The confirmation of the Kepler Void was a triumph of observational astronomy, a testament to the rigour and persistence of the scientific method. But it was a victory that opened a profound wound in our most cherished theories. The darkness in Cygnus was no longer just an absence of light. It had become the embodiment of a deep and unsettling ignorance, a direct challenge forcing us to question the very foundations of what we think we know about the origin, evolution, and ultimate fate of everything. And from that challenge, the most outlandish, the most creative, and the most desperate theories would begin to bloom. And so, with our most cherished map of the cosmos laid bare, the Kepler Void ceased to be a mere curiosity. It became an arena, a proving ground where the veracity of our entire cosmological understanding would be put to the ultimate test. On one side stood the reigning champion of cosmic theory, the lambda cold dark matter model, the elegant and powerful explanation for almost everything we see. On the other, a silent 3 billion light-year-long shadow that simply refused to fit. The challenge was thrown down not in journals or at conferences, but in the humming refrigerated hearts of the world's most powerful supercomputers. A desperate clandestine race began. Cosmologists became digital gods tasked with birthing entire universes inside silicon chips. Their goal was not to create life or new worlds, but to conjure a ghost, to see if the known laws of physics as encoded in lambda CDM could ever, even by a 1 in a trillion chance, sculpt a void of such terrifying emptiness and scale. They initiated a computational siege on the problem feeding their machines the fundamental ingredients of our universe: the precise amount of dark matter, the observed quantity of dark energy, the subtle quantum fluctuations from the Big Bang that were meant to be the seeds of all structure. They were giving their digital cosmos the exact same starting conditions our own universe had 13.8 billion years ago. Then they pressed run. Inside these processors, time accelerated to an impossible frenzy. 1 billion years of cosmic evolution flashed by in an hour of processing time. We watched as gravity, the patient, inexorable sculptor, began its work. Virtual dark matter, invisible yet potent, clumped together under its own immense weight. It formed a glistening, ethereal scaffold, the cosmic web. Along these shimmering filaments, ordinary matter, the stuff of stars and planets, and ourselves, was drawn in, coalescing like dew on a spider's web. Light from the first virtual stars began to shine. Galaxies ignited, swirled into majestic spirals, and were herded by gravity into colossal clusters. And between them, as the matter rushed to these cosmic highways, the voids began to open up. These were the expected voids, the natural consequences of gravity. They were the quiet countrysides of the cosmos regions of low density, but they were never truly empty. They were populated by rogue galaxies crisscrossed by tenuous gas filaments, and permeated by the gentle, persistent gravitational influence of the surrounding structures. In simulation after simulation, hundreds of them each, a slightly different roll of the cosmic dice, the story was the same. The digital universes bloomed and matured, creating a cosmic web that looked from a distance hauntingly like our own. But as the scientists zoomed in, searching for a Kepler-sized monster, they found nothing. Their simulations produced voids, yes, great voids even. But they were all a fraction of the size, their boundaries soft and ill-defined. They were deserts, not bottomless oceans of nothing. The problem was one of violence and speed. To create the Kepler Void, you don't just need to move matter out of the way. You need to do it with an almost impossible efficiency, evacuating a volume of space so completely that it defies the gentle, persistent pull of gravity that should be trying to fill it back in. It's the difference between draining a pond and instantly vaporizing a lake. Lambda CDM, for all its power, is a model of gradual gravitational accumulation. It lacks a mechanism for this kind of cosmic cataclysm, this profound and lasting expulsion. The simulations kept producing the expected static of random chance, the gentle hum of gravity at work. They could not, it seemed, scream. Weeks turned into months, then years. Terabytes of data swelled into petabytes. Each simulation that failed to produce the void was not just a failure. It was a positive result, a piece of evidence suggesting that the phenomenon we see in Cygnus is not a fluke. The improbability grew with each computer run, the odds stretching from 1 in a billion to 1 in a trillion, until the numbers became meaningless, an admission of utter defeat. The Kepler Void was becoming a ghost in the machine, a spectre that haunted the edges of every simulated cosmos. It was the monster their models could not create. Was it possible that the fundamental forces we had coded into our digital universes were missing a crucial ingredient, or worse, was one of them wrong? a subtle anxiety began to ripple through the community. The void was no longer just a challenge to a model, it was beginning to feel like a judgment. And it was then, at the height of this digital impasse with our theories backed against a wall of improbable odds, that everything changed. The universe, it seemed, was about to speak again. For a decade, a new generation of sky surveyors had been quietly, patiently drinking in the light from the heavens. One in particular, an ambitious project known as the Magellan Extreme Integral Field Survey, or MASIF, was different. It wasn't just another telescope designed to take beautiful pictures. MASIF was a celestial cartographer of the invisible. Its primary mission was to chart the one thing our simulations were built upon, but our eyes could never see the true large-scale distribution of dark matter. It did this by watching for ghosts. MASIF measured the light from hundreds of millions of distant galaxies far beyond the Kepler Void with unprecedented precision. As that ancient light travelled across the cosmos towards us, its path would be ever so slightly bent and distorted by the gravity of the matter. It passed both visible and dark. By analysing these subtle systematic distortions, a phenomenon called weak gravitational lensing, astronomers could reconstruct the gravitational landscape between us and those distant galaxies. They could in effect create a map of the unseen, a chart of the gravitational skeleton that underpins the universe. For years, the MASIF team had been painstakingly assembling this map, cleaning the data, eliminating errors, and preparing for its public release. And their initial survey area just happened to include the entire brooding expanse of the Kepler Void. The scientific community held its breath. This was the turning point. The simulations were a theoretical battleground, a fight between our ideas and a statistical phantom. The MASIF data was real-world evidence, a direct dispatch from the front lines. It would either throw our beleaguered lambda CDM model a lifeline, perhaps showing the void was smaller or less empty than we thought a trick of the light, or it would tighten the screws, confirming our worst fears with cold, hard data. The release of the first data package was an event felt in astronomy departments across the globe. As servers whirred and downloads completed, a new, far more detailed portrait of the great emptiness began to resolve itself on screens. The silence that followed was not of confusion, but of profound, unadulterated shock. The first revelation was the void's boundary. Our previous maps, pieced together from galaxy redshift surveys, had shown it as a vast, amorphous region of darkness. The MASIF data tracing the very edge of the underlying dark matter structure painted a terrifyingly different picture. The void's edges were sharp, impossibly sharp. Instead of gently fading into the surrounding cosmic web like a coastline meeting the sea, the boundary was a precipice, a sheer cliff, where the density of matter dropped by a factor of thousands over a cosmologically insignificant distance. It looked less like a feature sculpted by the patient hand of gravity, and more like the edge of a cosmic wound, a place where something had violently torn the fabric of space-time, and the scar had never properly healed. No simulation had ever produced a boundary so stark, so unnervingly deliberate. Then they looked inside. The region we had once called empty was revealed to be something far stranger. It was not a perfect vacuum. Weaving through the profound darkness were a few impossibly thin filaments of gas. But this was not the warm, enriched gas we find between galaxies in the rest of the universe. Spectroscopic analysis showed it was almost pure primordial hydrogen and helium, seemingly untouched since the first few 100,000 years after the Big Bang. It was pristine virgin material, a fossil from the dawn of time, colder and more tenuous than anything we had ever detected. And more bizarrely, these filaments were not random. They seemed to trace weak, ghost-like pathways that didn't align with the gravitational pull from the void's edges. They were following a blueprint that our understanding of gravity simply could not explain. Scattered along these ghostly tendrils were yet another impossibility, a handful of dwarf galaxies. But these were not like the dwarf galaxies that orbit our own Milky Way. They were spectral, wraith-like things composed almost entirely of stars with barely any detectable dark matter holding them together. We call them ghost galaxies. According to Lambda CDM, this is pure heresy. A galaxy, especially a small one, I cannot form without a deep gravitational well, a halo of dark matter to act as a seed. It's the essential ingredient. Yet here they were, a small family of impossible orphans adrift in the great dark, a direct contradiction to the foundational principles of galaxy formation. They were a fleet of ships with no ocean to sail on, a testament to a physics we did not yet comprehend. But the final devastating blow came from the primary mission of the survey itself, the map of the dark matter. As the full gravitational lensing data resolved, the ultimate horror was laid bare. We had always assumed the Kepler Void, like all voids, was simply a region with less matter. The massive data showed something fundamentally different, something that sent reverberations through the core of cosmology. The void wasn't just empty of galaxies and gas, it was empty of darkness itself. The vast, overarching dark matter halo that should have surrounded it, the gravitational basin that defined its existence, was thin. It was anemic, almost non-existent. The gravitational lensing signal, which should have been powerfully curved around the void's perimeter, was unnervingly flat. You have to understand the gravity of this discovery. In our standard model, dark matter is the alpha and the omega. It is the scaffolding. Its gravity is what pulls everything together. Ordinary matter, the stuff we see, is just the paint on the great invisible structure of dark matter. A void is supposed to exist because a region began with a slight underdensity of dark matter, causing the surrounding dark matter to pull everything away from it. But this was different. This wasn't a valley in the dark matter landscape. This was a place where the landscape itself appeared to be missing. It was as if the cosmic seed for this immense structure, the initial dark matter deficit, had been impossibly artificially large, or had been scoured away by some unknown force. The debate in the cosmological community intensified into a firestorm. The new data had not provided a resolution. It had provided a verdict. The Kepler Void was not a statistical fluke. It was not a ghost in the machine. It was a real physical entity whose properties, its sharp edges, its pristine internal filaments, its impossible ghost galaxies, and its shocking lack of a dark matter halo were not just improbable under lambda CDM, they were fundamentally incompatible with it. The model that had so beautifully explained the cosmic microwave background, the clustering of galaxies, and the expansion of the universe was now staring at a 3 billion light-year-long contradiction. It could not explain this place. The Kepler Void was no longer a puzzle. It had become a paradox, a place where the known rules of the universe appear to have been suspended. We were left standing at a precipice, our trusted map in tatters, looking out into an expanse of darkness that was deeper and more mysterious than we had ever dared to imagine. The question was no longer whether our model could be stretched to accommodate this anomaly. The question now whispered in laboratories and lecture halls around the world was far more terrifying. What new physics, what unknown cosmic force has the power to carve such a wound into the fabric of reality? And what else in the unexplored darkness are we about to find? And so we are left staring into this abyss, this gaping wound in the firmament etched into the constellation Cygnus. The data is unyielding, the emptiness is absolute. But it is not just a void in space that we are confronting. It is a void in our understanding, a chasm that has opened up beneath the very foundations of modern cosmology. For 2 billion light years, the universe as we know it simply stops. The silence from this region is deafening. It is a silence that speaks not of peaceful emptiness, but of a profound and unsettling error in our most cherished equations, a flaw woven into the very fabric of our cosmic story. The Kepler Void is more than a discovery. It is an accusation. It stands in silent judgment of our models, forcing us to ask a question that most scientists have spent their entire careers believing was already answered. Have we been fundamentally wrong about the nature of the universe? This is where the story turns from astronomy to inquisition. We must now place our most fundamental assumptions on trial, beginning with the grandest and most elegant of them all, the cosmological principle. For nearly a century, this principle has been our compass in the cosmic dark. It states that on the larger scales the universe is homogeneous and isotropic. In simpler terms, it should look roughly the same everywhere and in every direction. No matter where you are, your view of the cosmic ocean should be typical. There are no special places, no cosmic thrones, no chosen coordinates. This assumption is not born of mere philosophy. It is the bedrock of our mathematics. It allows us to take what we see from our tiny perch on Earth and extrapolate it across all of space and all of time. It is what gives us the power to speak of the universe as a single cohesive entity. The cosmic microwave background radiation, that beautiful fading echo of the Big Bang, seemed to be the ultimate proof of this principle. Its near-perfect uniformity with temperature fluctuations of just 1 part in 100,000 painted a portrait of a universe born in serene equilibrium. It was the comforting reassurance that our local cosmic neighbourhood was a fair sample of the whole magnificent sprawling creation. And then the Kepler Void, a structure so vast, so empty it spits in the face of this assumption. It is a profound violation of homogeneity. Imagine a perfectly smooth blue marble. That is our model of the universe. Now imagine taking a hammer and smashing a hole through its core, a flaw so enormous it compromises the entire sphere. That is the Kepler Void. This isn't a statistical fluke. It is a rebellion against the law of cosmic averages. A void of this magnitude should be, according to our standard models, a near impossibility, a 10 sigma event, a 1 in a trillion chance that strains credulity to its breaking point. So the first radical hypothesis emerges from the shadows. Perhaps the cosmological principle is simply wrong. Perhaps the universe is not the same everywhere. We could be living in an unusual matter-rich province of the cosmos, a kind of cosmic suburb bordering a vast and desolate hinterland. This idea, known as cosmic variance, has always been a possibility, but we believed it only applied on smaller scales. The Kepler Void suggests that the scale of this variance is monstrous, so large that our entire observable universe might not be a representative sample. It's a terrifying thought. It means our cosmic maps might only be showing us a single comfortable continent on a world filled with unknown oceans and strange lands. It implies that our universal laws, our calculated age of the cosmos, our understanding of cosmic destiny, might all be nothing more than local bylaws, parochial rules that don't apply out there in the great dark expanse of Cygnus. The universe we thought we knew could be just a tiny well-lit room in a vast, dark and unimaginably strange mansion. The void would no longer be an anomaly. It would be a borderland, a signpost telling us we have reached the edge of our familiar cosmic territory. It forces upon us a humility we have not had to embrace for centuries, suggesting that we are not just adrift in a uniform sea, but perhaps living on a privileged island, a fluke of cosmic density whose shores are lapped by an ocean of profound nothingness. This possibility alone is enough to send a chill down the spine of any cosmologist because it undermines everything we've built. It means going back to the drawing board armed with the terrifying knowledge that our view from Earth might be fundamentally biased. But what if the principle of homogeneity holds? What if there is a deeper reason for this wound in the cosmos? To find it, we must travel back in time to the very first fraction of a second of existence. We must examine the engine of creation itself, cosmic inflation. Inflation theory is one of the most successful ideas in all of physics. It proposes that in the instant after the Big Bang, the universe underwent a period of hyper-accelerated expansion, growing from smaller than an atom to larger than a galaxy in a heartbeat. This incredible stretching is what smoothed out the primordial wrinkles, ensuring the universe would be flat and uniform, just as we observe it in the CMB. Inflation is the great cosmic iron pressing the crumpled fabric of space-time into the smooth, predictable sheet we see today. It is the author of the cosmological principle, so if the principle is being violated, perhaps the author has a secret history. The Kepler Void forces us to ask a startling question. What if inflation wasn't perfect? What if it wasn't a universal, all-encompassing event? Our theories of eternal inflation already hint at this. They paint a picture of a multiverse, a bubbling foam of cosmic creation, where our universe is just one bubble among countless others. In this scenario, inflation is a process that stops in some places, creating a universe like ours, but continues raging in the space between. Could the Kepler Void be a scar from this violent process? Perhaps it's an echo of the pre-inflationary universe, a quantum fluctuation so colossal that even the phenomenal power of inflation failed to entirely smooth it away. It would be like a single stubborn mountain peak remaining after a global flood, a remnant of a wilder, more chaotic primordial landscape. Or consider an even more dramatic possibility. What if our universe, our bubble, collided with another in the distant past? Such a collision, a cataclysm on a scale we can barely imagine, would have sent shockwaves through the fabric of reality. It could have annihilated matter and energy across a vast region, splashing the contents of our cosmos aside and leaving behind a void, a cosmic bruise billions of light years across, marking the site of an impact from a reality beyond our own. This is no longer just a matter of observation. It is a search for a ghost in the cosmic machine. The void could be the fossilized evidence of an event that predates our familiar physics, a relic from the turbulent, untamed era of cosmic dawn. Looking into that darkness, we might be seeing the faint outline of a neighbouring reality, or the lasting damage from the birth pangs of our own existence. The very mechanism we invented to explain the universe's comforting regularity might have also authored its most terrifying exception. This path of inquiry transforms the void from a mere absence of matter into a dynamic historical artifact, a battlefield from a war fought in the first yoctosecond of time. It's a place where the rules of creation were tested and perhaps for a moment broken. And yet there are other whispers, other theories that are perhaps more unsettling still. They suggest that the problem isn't with the initial state of the universe, but with the very laws that govern its evolution. The crisis of the Kepler Void may not be a crisis of history, but a crisis of physics itself. We have to confront the possibility that the force shaping the cosmos, gravity, does not behave as we expect across these unimaginable distances. Our standard model of cosmology, called lambda CDM, rests on two pillars: cold, dark matter, the invisible scaffolding that pulls galaxies together, and lambda, the cosmological constant, more commonly known as dark energy, the mysterious force that pushes everything apart. We have measured the effects of these two titans with astonishing precision. We have watched them wage a war for the fate of the universe for 13 billion years, but our measurements have all been made inside the matter-rich parts of the cosmos. We have never been able to test our laws in a place so profoundly empty. What if the rules change in the quiet dark? Some audacious theories propose modifications to Einstein's general relativity. On the scales of solar systems and galaxies, Einstein's equations are gospel. But perhaps over billions of light years they begin to fray. These modified gravity theories suggest that the gravitational force might be stronger or weaker than we predict over vast empty stretches of space-time. In such a universe, the formation of structure would be different. Galaxies would clump together even more aggressively in some regions, effectively evacuating the surrounding space and creating voids far larger than our current models can account for. The void would not be a primordial relic, but a structure actively sculpted by a different, more powerful version of gravity. It would be a testament not to a flaw in creation, but a flaw in our understanding of the Creator's laws. Or perhaps gravity is fine, but the other side of the equation, dark energy, is the culprit. We call lambda a cosmological constant, assuming its influence is the same everywhere and at all times. It is the background hum of the universe, a constant pressure pushing space apart. But what if it isn't constant at all? What if dark energy is dynamic, a field that can have different values in different places? Imagine if within the region of the Kepler Void, the value of dark energy is far, far lower, or even zero. In such a place, the cosmic acceleration that dominates our neighbourhood would be absent. Without that outward push, the gravity from the surrounding superclusters would exert an even greater pull on any matter that was once there. Over billions of years, this gravitational imbalance would act like a cosmic siphon, pulling material out of the region and deepening the void moment by moment. The void would be a sinkhole in the cosmic energy landscape, a place where the engine of cosmic expansion has stalled. This is a chilling concept because it shatters the unity of the cosmos. It suggests that the fundamental properties of space-time itself can vary. If dark energy can vanish in one place, what's to stop it from changing here? What other constants of nature might prove to be merely local suggestions? The speed of light, the charge of an electron. The Kepler Void becomes a laboratory for a new kind of physics, one where the constants we hold dear are exposed as potentially fragile and variable. It forces us to question not just the map of the universe, but the very ink with which it is written. We look into that darkness and see the possibility of a different set of rules, a different physical reality coexisting with our own. This is a path that leads to a profound rethinking of everything we know, from the nature of the vacuum to the ultimate fate of the universe. If the laws of physics themselves are not immutable, then our neat, predictable cosmos dissolves into a far more chaotic and uncertain place. It's a place where anything could be possible, and that is a prospect both exhilarating and deeply terrifying. This staggering array of possibilities, a broken cosmic principle, a flawed inflation, a modified gravity, a variable dark energy, a collision between universes leaves us at a pivotal crossroads in the history of science. Each hypothesis is a doorway into a radically different conception of reality. On one hand, there are theories that try to save our existing framework, treating the void as an extreme statistical outlier, a black swan event that, while improbable, doesn't require a complete revolution. They argue for cosmic variance, suggesting the universe is lumpy on scales we never anticipated, but that the underlying physics remains sound. This is the conservative path, the one that seeks to mend the cracks in our foundation. It is a hope that our beautiful, elegant standard model is merely incomplete, not wrong. It asks us to accept that the universe is simply wilder and more varied than our limited perspective has allowed us to see. We are not special, merely living in a crowded province of a diverse and sprawling cosmic empire, and the void is just the first glimpse of a different kind of territory. On the other hand, there are the revolutionary paths. These are the theories that see the void not as a statistical fluke, but as a symptom of a deep sickness in the heart of modern physics. They argue that we are not just missing a piece of the puzzle, but that the puzzle box itself is shaped all wrong. They call for new forces, new dimensions, new interpretations of the very meaning of physical law. These ideas treat the void as a portal, a place where the familiar rules of our universe break down and give way to something else entirely. It could be the shadow of a neighbouring brain world predicted by string theory, its gravity leaking across the dimensions and pushing our matter away. It could be a cosmic texture, a topological defect in space-time left over from a symmetry-breaking phase, transition in the primordial universe like a flaw in a crystal as it cools. These are ideas born from the absolute frontiers of theoretical physics, concepts so strange they sound like science fiction. Yet the Kepler Void has given them a sudden shocking relevance. It has dragged them from the chalkboard and placed them squarely on the celestial map. This is the true crisis the void presents. It is not just one problem, but a cascade of them. It's a hydra of scientific uncertainty. For every question we answer, two more spring forth. The sheer existence of this colossal emptiness has shattered our consensus. It has divided the scientific community, pitting conservative interpretations against radical speculations. The void is a mirror, and in it we see reflected all the hopes, fears, and biases about our place in the cosmos. Is the universe a place of serene, predictable laws occasionally punctuated by extreme but understandable events? Or is it a place of deep abiding mystery, where the laws themselves are pliable, and reality is far stranger than we have ever dared to imagine? The darkness in the constellation Cygnus offers no easy answers. It only offers a choice. The theories are now on the table, a dizzying menu of possible universes. Each one offers a different explanation for the great emptiness. Each one leads to a different future for cosmology. But theories alone are not enough. Science demands evidence, and so the challenge is set. We must now turn our gaze back to the void, not with the tools of discovery that found it, but with new eyes, new instruments, new methods of interrogation designed to make this silent abyss finally speak its truth. We have to devise ways to test for the faint gravitational whispers of modified gravity, to search for the subtle temperature distortions of a cosmic collision, to find a way to choose a path forward from this bewildering crossroads. The silent emptiness is waiting, and the next great chapter in our cosmic story will be written by what we find when we listen to its silence, and so the battle lines were drawn. On one side stood a century of cosmological consensus, a grand and elegant edifice built from relativity and observation, the lambda cold dark matter model. It had explained the afterglow of the Big Bang, predicted the cosmic web of galaxies, and accounted for the universe's accelerating expansion. It was the triumphant hero of our cosmic story, the theory that had brought order to the chaos. On the other side there was only darkness, an impossible silent gaping wound in the fabric of reality. The Kepler Void. It was the single data point that refused to be reconciled, the stubborn, inconvenient fact that threatened to unravel everything. It was too large, too empty, too perfect in its desolation. Our best models, the very ones that painted the rest of the cosmos with such breathtaking accuracy, simply could not create it. They could not conjure a monster of this magnitude. For years, the community had been locked in this stalemate. Theorists proposed radical new ideas whispering of fifth forces or chameleon-like dark energy speculations that twisted and reshaped our fundamental laws. Observers meanwhile scanned the void's periphery, hunting for any clue, any anomalous motion, any faint signal from the dawn of time that might betray its origin. Yet every new survey only deepened the paradox. The void was precisely as empty as it appeared, and the galaxies at its edge were behaving exactly as they should, as if this unfathomable chasm were the most natural thing in the world. The standard model was on trial, and the evidence was damning. If it could not explain the largest, most extreme structure we had ever seen, then what was its ultimate worth? Was it merely a good approximation destined to be replaced by something deeper, stranger, and more profound? The heart of cosmology was in crisis, facing a chasm, not just in space but in understanding. Something had to give, and it would not in the heavens but in the heart of a machine. The final gambit was not a new telescope or a revolutionary theory, but an act of sheer brute force computational will. A global consortium of astrophysicists embarked on a project of almost unimaginable scale and complexity. Their goal was no longer just to simulate a universe, but to create a digital cosmos so vast, so detailed, so faithful to the laws of physics, as we know them, that it might by sheer statistical chance give birth to the very anomaly that haunted them. They called it the Legacy of Creation simulation. It was a desperate final attempt to see if the monster was truly a monster at all, or simply a 1 in a billion ghost, a phantom born from the machine of cosmic evolution. To understand what they were attempting, you have to picture this. Imagine not just a map of the universe, but a living, breathing replica. They began with a digital seed, a cube of virtual space billions of light years on a side moments after the Big Bang. This was not the smooth, uniform universe of textbooks. Instead, it was a roiling quantum foam seeded with the tiniest, most subtle density fluctuations, the very same ripples observed in the cosmic microwave background. These were the ancestral genes of everything that would ever exist. Into this digital genesis they poured the complete recipe of our reality. They added the gravitational pull of cold dark matter, the mysterious invisible substance that acts as the universe's skeleton. They programmed in the relentless accelerating push of dark energy, the cosmological constant that drives everything apart. But they didn't stop there. This was the simulation's great leap forward. They included the messy, complicated physics of us, of normal baryonic matter. Every star that would ever shine, every supernova that would ever explode was accounted for in the intricate lines of code. The way a quasar's ferocious radiation pressure could blast gas out of a nascent galaxy, effectively sterilizing it for billions of years. The way the shockwaves from colliding galactic clusters could heat intergalactic hydrogen to millions of degrees, preventing it from ever collapsing to form new stars. This was a universe with consequences where cause and effect played out over 13 billion years of simulated time. It was the most complete digital twin of our cosmos ever conceived. The simulation was so immense it couldn't run on any single machine. It was distributed across 3 of the world's most powerful supercomputers, working in concert, a trinity of silicon brains. For months they churned. Processors in Tennessee, in Japan, in Germany, collectively performing calculations on a scale that defies human intuition. Each machine tackled a different region of the virtual cosmos, passing data back and forth across dedicated networks, weaving together a single coherent timeline of cosmic history. They were not just solving equations. They were growing a universe from first principles, one quantum fluctuation, one gravitational interaction, one starburst at a time. The data streamed out not as simple numbers but as entire universes. Petabytes of information enough to fill libraries, and within these digital annals teams of scientists began their search. It was the ultimate needle in a haystack problem. They weren't looking for galaxies or black holes. They were looking for nothing. They were hunting for the signature of a truly profound emptiness. Algorithm after algorithm scoured the simulated data, searching for regions where the cosmic web had failed to form, where the relentless pull of gravity had been mysteriously thwarted. For the first year, the results were frustratingly familiar. The simulation was a resounding success in one sense, and a spectacular failure in another. It produced a breathtakingly realistic cosmic web with filaments, clusters, and voids that perfectly matched the statistical distribution of structures in our own universe. It was by all measures a perfect validation of the standard model, but it was too perfect. The voids it created were all within the expected range of sizes, hundreds of millions of light-years across certainly, but nothing that even approached the 2 billion light-year girth of the Kepler Void. The digital universe was playing by the rules. It refused to produce the outlier, the anomaly, the ghost. The mood within the collaboration grew tense. Had they spent years of effort and monumental resources only to prove once and for all that their theories were broken, that the model, no matter how exquisitely detailed, had a fundamental fatal flaw that prevented it from stumbling upon the kind of radical emptiness that nature had so effortlessly created? The whispers of new physics grew louder. Perhaps the answer wasn't in the code. Perhaps the universe's operating system had a secret function, a hidden variable they knew nothing about. Then, deep into the second year of analysis, a young postdoctoral researcher at the Max Planck Institute sifting through the data from Run 734 noticed something. It wasn't a colossal void. Not at first. It was a statistical peculiarity in the early simulated universe, a region just a few 100 million years after the Big Bang that was ever so slightly less dense than its surroundings. This itself wasn't unusual. Such fluctuations are the seeds of all structure. But this one was different. It was nestled in a unique cosmic geography. By a staggering coincidence, this underdense patch was almost perfectly surrounded by several regions that were by chance slightly overdense. In the digital cosmos, as in the real one, gravity is a game of tug-of-war. Matter flows from areas of lower density to areas of higher density. These surrounding overdense patches began to pull. Like cosmic shepherds, they started herding the sparse matter away from the central emptier region. The process was agonizingly, excruciatingly slow. For the first billion years of the simulation, the region looked like any other developing void destined to be of a modest, unremarkable size. But the simulation continued its relentless march forward in time, and the perfect storm of cosmic coincidences continued to build. The simulation showed that two of the surrounding dense regions evolved into massive protoclusters of galaxies. Their gravitational pull intensified, becoming vast cosmic anchors, dredging matter from an ever wider area. Meanwhile, another flanking region ignited with a furious wave of star formation, and the resulting stellar winds and supernova shockwaves acted like a celestial blowtorch blasting gas and dust away from the void's nascent boundary, further scouring it clean. You are witnessing a conspiracy of physics. Not a new law, but a terrifyingly precise alignment of the old ones. It was as if the universe had conspired, placing every gravitational source, every explosive event in just the right place, at just the right time to excavate a single region of space with ruthless efficiency. The void began to grow, and as it grew, its influence magnified. Dark energy, the constant outward pressure of space-time itself, works everywhere. But in the dense filaments of the cosmic web, gravity easily overpowers it, pulling things together. Inside a void, however, where matter is scarce, there is little gravity to fight against. Dark energy's push becomes the dominant force. The simulation revealed the final, crucial piece of the puzzle. As this void, born from a fluke of initial conditions and sculpted by a conspiracy of gravity, grew larger and emptier, it became a self-perpetuating engine of its own expansion. The dark energy within it began to push its boundaries outward more effectively than in any smaller void. It was a feedback loop. The emptier it got, the more dark energy dominated. The more dark energy dominated, the faster it pushed its boundaries outward, sweeping up the last vestiges of matter like a gravitational snowplow. It had gone rogue. It was no longer just a passive absence of matter, but an active, expanding bubble of space-time itself. The team watched transfixed as the numbers on their screens traced the birth of their monster. At 5 billion years, it was a giant. At 10 billion years, it was a titan. And at 13.8 billion years simulated present day, there it was, staring back at them from the heart of their digital universe. A region of profound, shocking emptiness. Its diameter, 1.97 billion light-years. Its matter density, less than a tenth of the cosmic average. It was the Kepler Void, not an approximation. Not something similar. It was a statistical twin. The simulation had done it. A profound collective silence fell over the scientific community, the kind that follows a verdict in a long and arduous trial. The standard model, lambda CDM, was not broken. It was in fact more powerful and strange than we had ever imagined. It didn't need new physics to create the void. It just needed a perfect hand of cosmic cards dealt once in a volume of space, so immense we could barely comprehend it. The Kepler Void wasn't evidence of our failure to understand the laws of nature. It was evidence of nature's capacity to use those laws to produce outcomes of staggering improbability. It was the cosmic equivalent of a royal flush, a hole-in-one, a lightning strike on a clear day. It was a black swan swimming in a sea of cosmic darkness. We had found the ghost in the machine, and in doing so we had affirmed that the machine worked. The resolution was at once deeply satisfying and profoundly unsettling. It meant our universe is a place where such extremes are possible, that for every region teeming with the vibrant life of the cosmic web, there can exist as a necessary counterbalance a desert of this scale. The void was not a violation of the rules, it was the ultimate expression of them. It was the sound of the universe playing out every possible combination, including the most lonely, the most desolate, the most extreme. The immediate crisis was over. Cosmology could breathe again. The textbooks did not need to be rewritten. But science is never truly finished. A resolution in one area inevitably casts a brighter, more focused light on shadows in another. And as astronomers turned their newest instruments like the exquisitely sensitive James Webb Space Telescope towards the real void's distant foggy edges, they were looking with new eyes armed with the simulation's predictions. They were checking the model, testing its remarkable success. They began to trace the faint ethereal filaments of primordial hydrogen gas that the simulation predicted should lie at the void's true perimeter, the cosmic shoreline of this great sea of nothing. And there, in the faintest whispers of light from the dawn of time, they found something else. Something the simulation hadn't predicted. The hydrogen clouds were there just as they should be. But they were moving. Not with the gentle outward flow predicted by the model, the simple exhalation of an expanding void. They were moving with a strange, subtle collective drift. A sideways motion, a sheer as if the entire edge of this gargantuan structure was being stirred by an invisible gravitational hand. It was a tiny discrepancy, a detail lost in the thunderous victory of the simulation's success. But it was there, a signal in the noise. The monster had been explained, its existence now plausible. But it seemed to have a faint, anomalous and utterly inexplicable heartbeat. The central conflict was resolved, but a new, more subtle mystery was just beginning to unfold on the shores of the great cosmic quiet. And so the silence that had so profoundly unsettled us begins to speak. The great darkness in Cygnus, the abyss that once stared back with an unnerving emptiness, has finally yielded its story. It was never a void of nothing but a repository of everything we had yet to learn. The answer when it arrived was not a monster lurking in the shadows, nor an alien artifact of impossible scale. It was in its own way far more magnificent. It was the universe itself revealing a facet of its character we had never before been forced to witness with such clarity. The Kepler Void was not an object in the cosmos. It was a feature of the cosmos, a natural albeit staggeringly vast consequence of the ceaseless gravitational ballet that has choreographed everything since the dawn of time. A monumental underdensity, a place where the cosmic web had failed to weave its brilliant filaments, leaving behind an echo of the primordial universe. This revelation, born from decades of painstaking observation and relentless computational modelling, did not close a chapter in our exploration. It threw the entire library open. We came to this patch of sky seeking a singular anomaly, and we departed with a fundamentally new calibration for the entire cosmic machine. Before this journey, our models of the large-scale structure were like elegant blueprints for a skyscraper, predicting with remarkable accuracy the placement of great superclusters, the luminous support beams and junctions of our universe. But the Kepler Void was a flaw in that blueprint, so profound, so impossibly large, that it forced us to question the very strength of the materials, and the foundational principles of the design. Its existence meant that the processes forming the cosmic web were capable of producing structures and absences on scales our theories had deemed statistically miraculous, bordering on impossible. Think of it as discovering a desert on Earth wider than any known continent. Such a discovery would compel geologists to rewrite their understanding of plate tectonics, of weather patterns, of the very history of the planet's surface. This is what the void did for cosmology. It provided a new extreme benchmark. It became a gravitational anchor for our simulations, a fixed point of such extremity that any viable model of the universe now has to be able to produce it or something very much like it without breaking. Models that once worked beautifully on smaller scales were suddenly stretched to their breaking point and many snapped. The survivors, the refined and more robust theories that emerged from this crucible of intellectual rigour, now carry within their code a deeper truth about the way gravity sculpts reality across unimaginable distances. They are more powerful, more nuanced, and they are stronger because they were tested against the silence. This grand recalibration rippled outwards, touching everything we thought we knew about the architecture of our existence. We began to see the universe not just as a collection of galaxies, but as a dynamic interplay between matter and its absence. The great voids, long dismissed as the uninteresting gaps between the cosmic fireworks, were suddenly revealed as essential characters in the cosmic drama. They are the counterweights to the great clusters, the engines of cosmic expansion, on a local scale, pushing galaxies apart and shaping the flow of the intergalactic medium. They are the dark rivers that guide the streams of galactic migration, defining the boundaries of superclusters with their gravitational emptiness. The Kepler Void, by virtue of its sheer record-shattering scale, became the ultimate laboratory for studying this delicate push and pull, a place where the subtle, pervasive influence of dark energy is laid bare, less obscured by the noisy gravitational chatter of matter. In this profound emptiness, the quiet hum of cosmic acceleration becomes the dominant sound, and by listening to it we can fine-tune our understanding of the force that will ultimately determine our universe's fate. But the legacy of this celestial enigma extends far beyond the elegant equations of theoretical physics. It is a profoundly human story. It is a testament to our own relentless, unyielding curiosity. It is a story about how we, a species confined to a fragile planetary cradle, can project our senses and our minds across billions of light years to confront a mystery and wrestle it into the light of understanding. It began with a subtle dimming, a statistical improbability in a flood of data from a telescope named for a man who revolutionized our view of the heavens 4 centuries ago. It was a ghost in the machine, a whisper that could have been easily dismissed as an error or a fluke, but a few inquisitive minds refused to let it go. They saw not an error, but a question mark hanging in the cosmos. What followed was a masterclass in the scientific method, a global, multi-generational effort that exemplifies the very best of our species. Astronomers on remote mountaintops spent sleepless nights, guiding colossal telescopes capturing photons that had travelled for eons from the void's distant edge. Theoreticians in university halls filled blackboards with calculations, their chalk dust settling like fallen stars as they built and dismantled miniature universes inside supercomputers. Engineers and software developers crafted new algorithms, ingenious new ways to sift through petabytes of data, searching for the faintest galactic signatures against the overwhelming black. It was a symphony of collaboration, a testament to the fact that the greatest challenges of cosmic discovery are not conquered by lone geniuses, but by a dedicated, interconnected community, united by a single burning question. Why is it so dark over there? This journey has taught us that the universe does not always shout its secrets. Sometimes it whispers them from the quietest, most unassuming corners of the sky. Our role is not merely to look for the brightest lights, the most violent explosions, or the most dazzling nebulae. It is also to listen to the silences, to map the shadows. To understand that absence itself is a form of information, that what is not there can be as instructive as what is. The Kepler Void has trained a new generation of astronomers to value the darkness, to see voids not as empty canvases, but as active, influential components of the cosmic ecosystem. We are now purposefully seeking out these immense underdensities, mapping their contours and plumbing their depths. for we now know they are not barren wastelands. They are pristine sanctuaries. Within these cosmic laboratories, the universe is stripped down to its most fundamental forces. Here in the profound isolation, individual galaxies evolve without the constant gravitational harassment from close neighbours. Their star formation histories are different. Their chemical compositions are purer. They are like lonely time capsules preserving a quieter, simpler mode of galactic life that has been erased in the chaotic crush of a supercluster. By studying these isolated inhabitants on the shores of the great voids, we can untangle the complex environmental factors that shape a galaxy's destiny. We can finally separate nature from nurture on a galactic scale, answering questions about how much of a galaxy's fate is written in its initial mass and how much is sculpted by the violence and richness of its surroundings. The Kepler Void offers us thousands of these control groups for our grand cosmic experiments, a gift of perspective we are only just beginning to unwrap. And this new perspective is already shaping the future of our quest. The next generation of telescopes, both on the ground and in space, are being designed with this lesson in mind. Missions like the Euclid Space Telescope and the Vera C. Rubin Observatory are not just hunting for brilliant quasars or distant supernovae. Their core mission is to create the largest, most detailed three-dimensional map of the universe ever conceived. They will chart the cosmic web with unprecedented precision, but just as critically they will map the voids that the web surrounds. They will find more structures like the Kepler Void, perhaps even larger ones, and they will populate them with the faint faraway galaxies that have so far eluded us. They will give us the statistical power to determine if the Kepler Void is a once-in-a-billion-years fluke, or a standard if rare feature of cosmic architecture. The answers these future missions provide will in turn feed back into our theories. Should we find that colossal voids are more common than our current leading model, the Lambda CDM model predicts it would be one of the most significant discoveries in modern cosmology. It could point to a new understanding of dark energy, suggesting its influence is not as constant as we believe. It might hint at a subtle modification needed in Einstein's theory of general relativity on the larger scales. Or it could reveal the signature of exotic physics from the very first moments after the Big Bang ripples, of which have been amplified over 13.8 billion years into the gargantuan structures we see today. The void in Cygnus, once a local puzzle, has become a potential key to unlocking the most profound secrets of creation and cosmic destiny. It has sharpened our questions, refined our tools, and pointed the way forward into a new territory of discovery. So when you look up now towards the constellation of the Swan, towards that specific patch of sky, where Kepler once hunted for planets, you're no longer looking at a simple absence. You're looking at a monument to scientific persistence. You're seeing a cosmic Rosetta Stone that helped us translate the language of the large-scale universe. You're witnessing a place that forced us to be humbler in our assumptions and bolder in our imagination. The darkness there is not an ending, it is a beginning. It is a challenge, a dare from the universe to look deeper, to think harder, and to never ever mistake emptiness for insignificance. It reminds us that every patch of sky, no matter how blank it appears, contains a story. And we, the curious inhabitants of a small blue world, have taught ourselves how to read them. Our journey does not end here. It never does. The resolution of one great mystery invariably illuminates the landscape of our own ignorance, revealing new and more subtle questions waiting on the horizon. The universe is a book of infinite pages, and with the story of the Kepler Void, we have not finished a chapter, so much as we have finally learned the alphabet needed to read the next. The quest is what defines us. It is the unbroken thread that connects the ancient stargazers charting constellations on cave walls to the astrophysicists modelling cosmic evolution on supercomputers. It is the simple, powerful and deeply human impulse to look up into the vast silent night and wonder, to ask the audacious questions, and then with ingenuity, with courage and with a hope that transcends generations, to set out together to find the answers. The cosmos awaits, and we are and always will be explorers.